Hello and welcome to this 13th session of Symmetry in Chemistry. Last time we were looking at atomic orbitals, and this time now we're going to get onto molecular orbitals. And we're going to construct molecular orbitals from the atomic orbitals as our starting point, using these so-called SALCs, these symmetry adapted linear combinations. So this means linear combinations, this means summing up the atomic orbitals, and we're going to be summing them up in particular combinations that correspond to the symmetry of the representation. And so what we're used to doing now is we're used to taking for example, external atoms in a molecule of methane, for example, and actually creating a representation, which is to say how those atoms behave under all the operations of the group. And so once we've done that, we reduce it to the irreps, and we compare those irreps with the irreps that correspond to the atomic orbitals on the central atom, and where the irreps match up, we find a bonding interaction. Now ultimately, to write a wave function, we're going to need to find some linear combinations of the external atoms. So for example, the 4H atoms in methane, we'd need to find combinations of the 4 different wave functions that conform to the symmetries of the different irreps that are involved. And so the way we do this is we project the symmetry operations and the characters for the particular group that we're working with onto one of the atoms. And so the result of all the operations and characters being, as it were, mapped onto that atom will give us a whole series of other atoms in the combination that corresponds to that symmetry. Probably easiest to do through an example. Actually, what we've got on the scheme, the scheme we've got on the screen at the moment, we've got a molecular orbital diagram for a diatomic. And actually, normally with a diatomic, this is kind of done through just sort of geometric logic. That's to say, sigma orbitals, remember we learned these are the head-on overlap of orbitals, whereas pi orbitals involve the sideways overlap, and how we see bonds as where we have regions of electron density between the nuclei, and antibonds where we have nodes between the nuclei and regions of electron density outside the nuclei. So that's the normal way we'd go about describing a diatomic molecule. But interestingly enough, one thing we'll be able to do later on is we'll be able to see you could actually derive all this from group theory as well. But it's slightly more complicated because with a diatomic molecule, you're in that kind of infinite scheme where you might have a group like D infinity H, where you could have an infinite number of rotations. That just makes life a bit more difficult. So if we can look at a tetrahedral example. So we've already looked at methane a little bit, and you can see in the table on the right hand side, we've got the tetrahedral character table, and underneath that we've got the representation for the 4H atoms in methane. So we know already that those 4H atoms transform as A1 plus T2. We also know that the s orbital has A1 character for the central carbon atom, and the 3 p orbitals have T2 character. Now, in terms of these linear combinations, we can perhaps immediately deduce that the fully symmetric combination must be the most kind of symmetrical way we can combine the 4 orbitals of hydrogen, and that's just simply to add them all up with equal weighting. So phi1 plus phi2 plus phi3 plus phi4, this would represent the most symmetrical combination. But life gets a bit harder when we try to consider what would be the symmetry adapted linear combination of hydrogen orbitals if it's going to correspond to the T2 irrep symmetry. So the way we do this, in the tetrahedral group, we know that the order of the group is 24. There are 24 different operations. We just choose a random atom, so for example H1, a random hydrogen atom, and we simply apply all 24 operations to that hydrogen atom in turn. And when we do that, we end up with this long series of results here. And of course, the other thing we're supposed to do is in order to project the symmetry of the irrep, we are going to have to multiply the orbitals involved by the characters for the particular operation. So for example, if we're looking to do T2, if we look at the T2 row in the character table, the first character is 3 for the identity, for the E operation, the do nothing operation. And so that's why, starting using the first hydrogen atom, phi1, at that atomic orbital as our starting point. That's why the first term we've got here is 3 phi1. This is because obviously the hydrogen atom 1 stays put if we are doing the identity operation, and because the character is 3, we multiply it by 3. So we start off with 3 phi1. Going along the row, so the next operation is S4. And so there are 6 of these S4s. And that's because we've got 3 S4 axes. These are the X, Y, and Z axes. And we can do the S4 clockwise or anti-clockwise. So we've got 6 of these operations to think about. And on top of that, the result has to be multiplied by -1, which is the character for T2 under 6S4. So if we took the hydrogen atom H1, we have to think, how is that going to behave under S4? Well, if you think about it, the X, Y, and Z axes are all going to point in between these atoms. And so if you can imagine an S4 axis bisecting H1 and H2, if we rotate that 90 degrees and then reflect that in a perpendicular plane, depending on whether you go clockwise or anti-clockwise, it's going to go into H3 or H4. So H3 and H4, let's say phi 3 and phi 4, are 2 possible outcomes. But of course, we do have other axes as well. And so taking a perpendicular axis, you'll find that, so for example, let's have a look. If we took the axis between H1 and H4, then those S4 operations will map it to H2 and H3. And so the other axis would be between H1 and H3, and they would map it across to H2 and H4 when you do those operations. So the point is that every single one of these operations moves the hydrogen onto a different atom. And because we're doing clockwise and anti-clockwise, and because the S4 axis goes through all 3 Cartesian axes, essentially the results of the 6 operations are moving it onto the other 3 atoms, but on 2 different occasions. And so that's why we've got 2 phi 2, 2 phi 3, and 2 phi 4 in the brackets, and there's a minus in front of the brackets because that's the character. So next up, we've got the 3C2. And again, because the character is -1, we've got a minus sign in there. And then when we apply the C2 operation, that can move H1 onto H2, or H1 onto H3, or H1 onto H4, depending on which of the 3 Cartesian axes we're rotating around. And so phi 2, phi 3, and phi 4, again, are the possible outcomes. So again, each of these rotations are moving the hydrogen atom onto a different atom, and depending on which Cartesian axis involved, it takes you onto a different hydrogen atom, hence the phi 2, phi 3, phi 4, all of them having a minus sign in front because of the character. Next up, we've got the C3 rotations, but you see that the character for this is 0. So there's no point working out where the hydrogen atom goes under the C3 rotations because it's all going to be multiplied by 0 anyway and will disappear. So we can jump ahead now to the 6 sigma d. And so these sigma d planes, these are going to bisect the different combinations of atoms. So for example, we could have an H1 and an H4. Those 2 atoms can have the sigma d in. So actually, it's an interesting one, this, because the planes take in 2 of the hydrogen atoms, it does mean that 3 of the 6 planes will actually hold the H1 atom. Think about the different ways you can get pairs of atoms. So actually there are 6 ways that you can pair up 4 atoms. So that's 4 factorial over 2 factorial, 2 factorial. So there are 6 different pairs of atoms, and so 3 of those pairs will have H1 in the pair. And if it's got H1 in the pair, that's to say that the mirror plane goes through H1, then H1's not going to move. And so for 3 of those sigma d operations, H1 is just going to give H1. And that's why, interestingly enough, when you look at the outcome here, you've got a plus in front of the bracket, and that's because there's a +1 character, and then you've got 3, 5, 1. So for 3 of those dihedral mirrors, you have the H1 just staying there, just going from H1 to H1. And then the other 3 mirrors, which these are going to involve pairs of hydrogen atoms that don't involve H1. So you could have 2 and 3, 3 and 4, and 2 and 4. And so in each of these cases, in those 3 cases, the hydrogen atom is going to get reflected onto a different atom. And depending on which of the 3 mirrors it is, it's going to get reflected onto one of the other atoms, H2, H3, and H4. And that's why in the bracket there, we've got 3, 5, 1, plus 5, 2, plus 5, 3, plus 5, 4. So we've worked out the result of all 24 operations, starting off with hydrogen 1, or the wave function phi 1, for the orbital on hydrogen 1. And so what we do now is we just add them all up, add them all together, and they all add up to 6 phi 1 minus 2 phi 2 minus 2 phi 3 minus 2 phi 4. And so what really matters here, it's the relative sizes and the relative signs of the coefficients in front of these different orbitals. So the absolute numbers, actually we can tweak those later on. As I say, it's just the relative values and the signs that matter. So expressing them in terms of the simplest whole numbers, the simplest integer ratio, this would be 3 phi 1 minus phi 2 minus phi 3 minus phi 4. Now the next tricky bit is that because T2 is triply degenerate, that means ultimately there need to be 3 separate wave functions, which taken together gives the triply degenerate state. So triply degenerate means it's actually describing 3 different wave functions which all have the same type of symmetry, and so they'll all be of equivalent energy. So what we've done is we've at the moment created one of these functions with the 3 phi 1 minus phi 2 minus phi 3 minus phi 4. So when you think about how you can make alternative ones which are comparable, the obvious thing to do would be to start from a different hydrogen atom. We started from H1 last time, you might have started at H2. But using this method, because there are 4 different H atoms which are all sort of equally valid, this will actually generate for us 4 different symmetry adapted linear combinations, whereas what we want are 3. And to make life more difficult, it turns out that we can't really just choose these 3 randomly, because there is a particular requirement that we've got to be concerned about. Just before I tell you about that, if we look at this last point here, you can see here that having started on H1, the phi 1 is weighted 3, and the other 3 atoms are weighted 1 relatively with a sign change. So as you can predict straight away then that starting with H2, that would give you 3 phi 2 and then minus 1 of all the others. And so you can say the same thing about phi 3 and phi 4. So we don't need to go through the whole process again. I mean, you can if you like, just to check. But these are the 4 functions that we get. But this isn't the final answer just yet. Right, so having got 4 functions potentially that are symmetry adapted linear combinations, we somehow need to get 3 so-called orthonormal SALCs. So orthonormal, that's a contraction of orthogonal, so that they're mutually the dot products will come out to 0, and normalized, which is effectively the length of the vector. It has to be 1. We'll look at how to do that now. So there isn't actually a fixed way of doing this, and in practice it's often most easily done just by adding and subtracting functions and just seeing what works best. So for example, if we just take the H1 function, and this is to say when we were based with H1 as our starting atom, if we just add that result to the other 3 atoms sequentially, then we actually get something that looks quite sensible, which are these functions written here. And so what I've done here actually is I've just divided through by 2. When you actually add H1 onto the others, they all have a 2 in front of them. And I've just divided that out. And so you can see here that we've got a kind of a pattern where, looking at these 3 linear combinations, all of them involve 2 pluses and 2 minuses. And so there's a kind of symmetry to that. So you might think, how many ways can you have 2 pluses and 2 minuses in front of 4 functions? So I think that's 4 factorial over 2 factorial, 2 factorial. So that would appear that there's 6 ways of doing it. So you might think, well, hold on, what are the other 3? We've got 3 here. So in fact, the other 3 ways you could do it is you could just put a minus sign in front of the whole wave function in brackets. And maybe 3 alternative ways of doing it. But in actual fact, just putting a minus sign in front of the whole wave function in brackets, that doesn't really make any physical difference. Because ultimately, when you're doing calculations based on these wave functions, and you're effectively working with the squares of the wave functions, that minus gets changed into a plus anyway. So very often we say with these wave functions, we sort of work it out to within a phase factor. And so that plus or minus often doesn't make a huge amount of difference when we're looking at the properties of the wave function. So we can just stick with those 3. And so, as I say, their products must be 0, and we can just check this. So for example, if we take the first 2 combinations, when you multiply them together, all the cross terms go to 0. So we just define these orbitals so that the only non-zero terms are going to be the like terms. So phi 1, phi 1. So taking those first 2 linear combinations, they're both positive, so that would give you a positive result. Whereas looking at the phi 2's, the first phi 2 is positive, but the second one's negative. So that product of those 2 will be negative. Likewise, phi 3 is negative, positive, so that product will be negative. Phi 4 and phi 4, they're both negative, so their product will be positive. So you multiplying all these together, you get 2 plus 1s and 2 minus 1s. And so when you sum them up, they come to 0. And you can try the same thing with the other combinations. They're all mutually orthogonal. So this is what we want in these linear combinations of atomic orbitals. They're all meant to be orthogonal to each other, all following on from our orthogonality theorem that underpins it all. And there's also the question of the normalized. And so the constant that we're free to put a constant in front of these expressions, and we choose a constant so that ultimately it's normalized to 1. So that means ultimately if you multiply the linear combination by itself and integrate it up over all space, the answer should come to 1. So for example, if we take the first linear combination and multiply it by itself, of course all the minuses turn into pluses, because obviously a minus times a minus is a plus. And so we just take the like terms, and so the phi 1, phi 2 and phi 3 and phi 4, those like terms will ultimately each give plus 1 in the product when it's all integrated up. But of course once you sum those 4 plus 1s, you will get the answer of 4, and that's not normalized to 1. So the kind of recipe that you do is you put a constant in front of these orbitals, and that constant is 1 over the square root of the sums of all the squares of the coefficients. And so for example, a nice example to look at, for example, if we look at this combination like we've got in the first T2 there, if we put a half in front of that linear combination, then when you multiply it by itself, the half phi 1 times a half phi 1 will give you a quarter of phi 1 squared. And so it means that ultimately that you get a quarter in front of each of those 4 1s. And so that hence quarter plus quarter plus quarter plus quarter is 1, so it's normalized to 1. And that half there, you can see that that half, that is 1 over the square root of the sum of all the squares of the coefficients. So all the coefficients are 1 or minus 1, they all square to give plus 1, and they all sum up to give 4, and so 1 over the square root of 4 is a half. So likewise with the A1 linear combination, that would normalize up in just the same way, And it's just the same kind of combination, except there's some minuses in there, but of course they'd multiply by themselves to give pluses. Now, looking at the octahedral case, this might be slightly more difficult. So in the octahedral case, we've got a bigger group now, and we've got 6 ligands this time, looking at, for example, an octahedral complex. So we've got 6 ligands, and they give the reducible representation shown right at the bottom of the table there. So you can see, for example, the character for the identity representation is, the identity operation is 6, and this is because we've got 6 ligands as our basis. So the character there, they all stay put, so they all contribute 1 to give 6. And so we can work out here all these different other characters. So you can see that some of these are zeros. So those zeros, these correspond to symmetry operations where all the atoms move. So those threefold rotations, those atoms all move. The 6C2 prime, so those 6C2 primes, they are where the C2 axis is bisecting the corners, so all the corners are going to be moving around there. Centre of inversion moves all of them. Similarly, the S4s move them all, and the S6 is just the same. The C4 axes. So with the C4s, obviously the axis is going to go through the 2 axial ligands, so they stay put, and the other 4 move, giving you this character of 2. And same thing with the C2. The C2 axis will be a Cartesian axis, which will go through 2 of the atoms and leave them unchanged as well. The sigma H, that goes through 4 equatorial ligands, so those 4 don't move. And likewise the sigma Ds there, the sigma D will cut through 2 of the ligands, and so those 2 don't move. So that makes sense of all the characters for the gamma representation for the 6 orbitals, for the 6 ligand orbitals. Then they reduce to A1G, T1U and EG going through our reduction process. So as I've got up on the screen here, we can perhaps just kind of deduce that the fully symmetric combination is bound to be just the simplest sum of all the 6 ligand orbitals. And we have this 6 to the power minus a half so-called normalization constant. So you remember that means that's 1 over the square root of 6. So that means once we multiply the wave function by itself, that'll become 1/6. And so that we'll have a 1/6 in front of each of these products, and so they'll add up to 1, normalize the wave function. Now for T1U, this is quite hard work because we've got 48 symmetry operations. We've got order of the octahedral group is 48. So we need to go through all of this, a bit like we did before. So with the T1U case, same sort of thing. We choose one of the ligands randomly. So for example, H1. So we can see that on the picture. We can start there. And then we're going to go across the characters. So if we find the T1U irrep, the first character 3 is for the identity operation. And so clearly H atom doesn't move, H1, so we just returns phi1, and we have a 3 in front of it because that's the character for that particular element there in the table. Then we move on to 6C4. So again, we've got 3 C4 axes, the Cartesian axes. We can rotate clockwise or anti-clockwise, and we just have to go through all this process for the all 3 axes. And so we can see in the case of T1U, we've got a 1 for that character, so that explains the plus in front of the brackets. And then just moving along the row there, so you see next character's -1, so we've got a minus in front of the 3 C2 operations. Then we can actually forget about the C3 operations because there's a 0 for that character. Then onto the C2 prime, so these C2 axes will then bisect the ligands rather than being on the Cartesian axes. And then we're on to I, reflecting through the centre of the origin. And rather than going through every single one of these, as we did this before in a previous example, you can simply see that we're just collecting where H1 moves to using each of these operations in turn. And then once we add them all up, it comes to 8 phi 1 minus 8 phi 4. So again, we can express this as the simplest integer ratio, making sure that the relative signs are still there. So that just becomes phi 1 minus phi 4. And so again, if you consider the ratio, the relationship between phi 1 and phi 4, we started with the hydrogen atom 1, the ligand 1 rather. And then what dropped out in the end was that same ligand 1 minus the opposite ligand 4. And so really that guides us to what we would get if we select other ligands. So for example, we'd get phi 2 minus phi 5 and phi 3 minus phi 6. And then, in fact, if you could then say, well, why not start with phi 4, phi 5 and phi 6? And in fact, all that would give you, it would just reproduce these three functions, except you just have a minus in front of them. And as we said before, the minus in front of them isn't really that physically important anyway. So we can stick to just these three functions as being our triply degenerate T1U symmetry adapted linear combinations. And because there's just two functions with a sort of unwritten 1 in front of them, then the normalizing factor will just be 1 over the square root of 2. So once those are multiplied by themselves, that would become a half, and summing those two half terms would give you the normalized function. And so what's interesting about this is that when you look at these functions, because these functions involve 1 and 4, which are opposite each other, 2 and 5 that are opposite each other, and 3 and 6 that are opposite each other, these actually define the Cartesian axes, because we define the x, y and z axes in this octahedral complex as going through pairs of ligands. And actually the other thing as well is that you can consider there to be like a plus x side and a minus x side in your sort of x, y, z axes concentrated at the origin. And in fact, we see the same thing here. We've got a plus and a minus, so that is plus phi 1 minus phi 4. So just like the x-axis will have a positive direction and a negative direction. And so it's not surprising, therefore, that this T1U combination here is also the combination, the symmetry irrep that describes the x, y and z axes, these directions. Now we can go through the same process with the Eg, for the Eg symmetry adapted linear combination. So again, going through this sort of slightly tiresome process of starting with hydrogen atom H1, then we find the row Eg in the character table. So we can see it starts 2 phi 1, where the identity hasn't moved the phi 1 atom, and we multiply it by 2 because that's the character for the identity operation. And then we simply go through all of these 48 operations, which we've done there, gather together all the terms, then we put their sort of lowest, then we get the sort of lowest common denominator integers, and so we end up with 2 phi 1 minus phi 2 minus phi 3 plus 2 phi 4 minus phi 5 minus phi 6 minus phi 6. So again, you can see, again, there's a kind of a pattern here. So we've started off on the ligand 1, and so that's come out with a 2 in front of it and positive. Then the opposite ligand has also come out with a 2 in front of it and positive, and all the other 4 ligands have come out with a minus 1 in front of them. And so we could predict what would happen, therefore, selecting other atoms to go first with all these different operations. So we've got them here on the screen. These are the different versions of it, say starting with H2 and H3. And so again, playing around with these, if we subtract the second one from the first one, then we get some cancellation, and that would leave you with phi 2 minus phi 3 plus phi 5 minus phi 6. And what's nice about this is that this turns out to be orthogonal to the original one. So if we go back to the original one, 2 phi 1 minus phi 2 minus phi 3, etc. Then when you look at the phi 2 combination, we've got a plus 1 and a minus 1, comparing the two functions. So they multiply together to give minus 1. Then the phi 3 and the phi 3 are both negative, so they'd multiply to give plus 1. The phi 5, that's a plus 1 and a minus 1, so they multiply out to give minus 1. And the phi 6, they're both negative, so they multiply out to give plus 1. So ultimately we've got 2 plus 1s and 2 minus 1s. So this combination here, which we've got here from subtracting the second from the first of these two alternative ones, the H2 and the H3, this turns out to be orthogonal to the first. So we actually end up now with two symmetry adapted linear combinations which are orthogonal one to the other. And we can normalize these. So just like we'd had before when we had a series of 4 atomic orbitals, half in front of them all normalizes it. But in this next case, you can see here, when we sum the squares of the coefficients, those 2's both square to 4. 4 plus 4 is 8. And then these other ones square to plus 1. So those 4 added onto 8 give you 12. And that's the origin of the 1 over root 12 we've got as the normalizing factor. So this is quite interesting. So when you look at what these represent, so one of these is going to be the z squared orbital. So think about like dz squared. And so you can see here that the this longer linear combination, which has got 2 phi 1 plus 2 phi 4, well, the 1 and the 4 ligands are opposite each other on a particular axis, which would be like the dz squared axis. And they're also the same sign. And of course the dz squared orbital is even parity. So those two opposite lobes on the dz squared are the same phase. So this lower sequence there, that represents a dz squared orbital. And then looking at this other combination, phi 2 minus phi 3 plus phi 5 minus phi 6. So you can see here the 2 and the 5 are both positive, and they're opposite each other, and they're perpendicular to the 1 and the 4 that we had from the previous orbital. And then the other ones, 3 and 6, they're also opposite each other, perpendicular to the 2 and the 5, and they're the opposite sign. So again, that's consistent with x squared minus y squared. And so yeah, the squares there representing the fact that the 2 and the 5 are the same sign, and the 3 and the 6 are the same sign, and the minus coming in there because the 3 and the 6 are the opposite sign to the 2 and the 5. So it's quite neat how these different signs and the different coefficients in front of these orbitals for the ligands actually kind of reflect the symmetry that we get on the d orbitals on the central metal. And so this is going to lead to the bonding interactions that we find in the transition metal complex. So, having worked through tetrahedral and octahedral, we can have a little look at water. And I'm just going to leave this as an exercise. And so I'll just take you through what you really need to know to work out the symmetry adapted linear combinations for water. So first of all, taking the water molecule. So the water molecule, we should say what its symmetry elements are. This should define what point group it is, and from there the character table. So in the water molecule, we've got this, obviously the identity is there. We see it's got a twofold rotation axis, and it's got two symmetry axes, two mirror planes, one in the plane of the screen and the other perpendicular to the plane, bisecting the two H atoms. And so that collection of symmetry elements is our C2V point group, and we've got, and of course in practice we just look up these point groups, and so there's the point group on the screen there. And so we've got these just 4 one-dimensional irreps, and of course that makes life a bit easier having a one-dimensional irrep. then you don't have to go through all the bother of all this kind of picking orthogonal combinations like we did with the E and the T representations, the reps. So in terms of the axes, we would take Z to be the principal axis. So it would bisect the two hydrogens and be the twofold rotation axis. And then the way we'll define the axes, we'll have the H atoms in the XZ plane. So you can think about it like the x-axis pointing to the right, y-axis coming out towards you, and the z-axis going up. If we center the coordinates on the oxygen atom. And so when you consider the pz orbital, so this is the orbital sitting on the oxygen atom, which is in the plane of the screen, sort of going up and down. Curiously, this one is invariant under all the operations. Obviously it is under E, but that C2 rotation leaves it unchanged. And of course those mirror planes just cut through that orbital and so leave it unchanged as well. So that 2pz orbital must have the A1 irrep symmetry. That's to say the fully symmetric irrep. And so then what we can do is look at the other orbitals on the oxygen atom. We've got the px and the py orbitals, and we can work out what they correspond to. Then we can consider the H atoms. And so again, we'd consider them together, and we've got to find some representation for those two atoms acting together under all the operations of the group, thinking about how many atoms remain unchanged. And then once we've got that representation, we'll have to reduce it to find what C2v irreps describe the two H atoms. Then we're going to ultimately have to work out, using our symmetry adapted linear combinations, what the combinations are for those particular H atoms that conform to the particular symmetries. And so once we've worked out all those linear combinations, all the symmetries, we'll then be in a position to put together the MO diagram. So this will be an exercise I'll leave to you for next time.